1942. Man achieves the first sustained nuclear chain reaction. 1945. Nuclear science expands. The first release of awesome destructive energy, an atomic explosion. 1946. Studies investigate the practicality of nuclear energy for the propulsion of aircraft. The birth of NEPA. 1956. The Atomic Energy Commission and the Air Force undertake the development of a nuclear reactor for the propulsion of a supersonic missile under the name Project Pluto. 1958. Further encouragement for nuclear-powered missiles. The initiation of winged missile system studies. 1959. As a result of these studies, the Air Force establishes a system development requirement for a supersonic low-altitude missile. 1960. The weapons system development is deferred, pending nuclear reactor feasibility. Lawrence Radiation Laboratories develops the Torrey II reactor series. Chance Vaught explores aerothermodynamic principles. Marquardt Corporation probes non-nuclear aspects of the propulsion system. 1961. The Torrey IIA reactor operates at full design power with overwhelming success. 1962. The Air Force proposes a flight test program, later deferred for ground testing of the nuclear Ramjet engine. A reduction in funds postpones the initiation of the concept. Navy interest leads to a study effort called Project Sinbad. 1963. The nuclear Ramjet technology program, formerly Pluto, is renamed Low Altitude Supersonic Vehicle, LASV, with consideration given to both nuclear and chemical modes.
As Air Force Director of this program, I welcome the opportunity to introduce the technical highlights that will be viewed in this film. This report reviews the Air Force's 7th year of advanced technology efforts aimed at proving the feasibility of the development of a nuclear ramjet-propelled supersonic low-altitude vehicle. Some of the efforts conducted last year are represented by, first of all, this model portraying our configuration analyses, a wind tunnel model to measure aerodynamic drag forces and lift forces, computer technology, circuits designed for micro-miniaturization and reliable operation in a nuclear radiation environment. The technical data, the test objectives, the test results and conclusions are all contained in 26 technical volumes now published as an Aeronautical Systems Division technical report. And now for a more detailed review of the highlights of this film.
One of the first steps in the initiation of the LASV-N1 program was the assembly of an industrial team with diverse capabilities for handling the varied aspects of system and subsystem development. As a result of its technical experience and background in the field, LTV, as prime contractor, invited over 350 companies to participate in the competition. Of these, 27 firms and additional consultants in special areas were selected as members of the team. The prime objective of this contract effort was to develop and test many of the components of subsystems required for a nuclear-powered vehicle capable of low-altitude penetration of defended areas at supersonic speeds with great accuracy at a cost advantage over comparable weapon systems. At the award of the contract, the dual approach to inlet development was employed. The Marquardt Corporation, the propulsion system subcontractor, conducted comparative studies of axisymmetric and double scoop inlets. Through detailed analysis of wind tunnel data, Marquardt and LTV independently recognized the value and advantage of the double scoop design. By mid-contract period, a joint recommendation was made to the Air Force to discontinue the axisymmetric inlet and pursue the scoop development, which offers advantages in the areas of external drag and simplified controls. After careful evaluation of the data, the Air Force redirected the inlet development effort to the singular approach. Marquardt also conducted a flow field survey to define the local inlet flow characteristics generated by the vehicle forebody over a range of free stream Mach numbers and vehicle angles of attack and yaw. A variable position flow field survey rake was located at the simulated inlet capture station. The rake consists of 5 cones and 2 wedges, positioned to determine the local Mach number, the flow direction, and the pressure recovery that occurs at discrete points in the inlet capture plane. In addition to the flow field survey test, 3 interchangeable double scoop inlets were designed for test on the 1500th scale inlet model. These inlets, designated B, C, and D, are fixed geometry type, with a starting door located on each side of the inlet vertical center line. Each inlet has a unique set of internal lines. The first 2 inlets, B and C, are based on experimentally determined lines derived from previous test results. The third inlet was developed from an analytical study using the method of characteristics for supersonic flow analysis. Evaluation of the inlets was conducted at LTV's high-speed wind tunnel and was based upon pressure measurements taken at the inlet throat and the subsonic duct. Performance was obtained as a function of inlet boundary layer bleed and over a range of Mach numbers, angles of attack, and angles of yaw. At design conditions, a throat pressure recovery of 88% of free stream was obtained. At the subsonic duct, a corresponding recovery of 86% was obtained. Other aerodynamic testing programs at LTV included the development of a new captive trajectory testing system, a unique device to rapidly obtain trajectories of the separating boosters. The usual model support sting is replaced by a hydraulically powered servo mechanism, providing 6 degrees of freedom for the booster model relative to the parent model. Also included in aerodynamic testing were 3 tests for gathering data related to nuclear weapon separation and delivery. The first test, performed at the ASD Gas Dynamic Facility, determined basic aerodynamic data for use in analysis of the trajectory of the store after it has left the cavity. The store model was statically positioned through 360 degrees angle of attack at Mach numbers from 0.5 to 3. The second test, performed at the LTV high-speed tunnel, determined store forces and cavity temperatures and pressures as the store was statically positioned at points along its predicted emerging trajectory. The third test, performed at the LTV high-speed tunnel, used a series of dynamically scaled stores which were ejected from a cavity to obtain transient cavity temperatures and pressures induced by the rapid ejection, and to determine store behavior during separation. An internally ducted scale aerodynamics model was tested approximately 280 hours during development of the missile configuration. The tests were conducted in the contractor and government wind tunnel facilities. The model was constructed to permit evaluation of the component contributions by a model buildup. Tests ranged from Mach 0.5 to 3.6 for the nominal clean and boost configuration. Alternate missile configurations using stabilizers of different size and arrangement were also tested to determine the most efficient aerodynamic configuration. The booster configuration test, conducted in the NASA Langley 16-foot transonic wind tunnel, determined missile boost characteristics over the transonic Mach number range. All three tests yielded data which agreed with earlier analytical results. The dynamic model program continued the LTV effort on the SLAM-3 program, in which the model was designed and fabricated, and wind tunnel testing initiated. For the present LASV-N1 program, protective plates were installed to enclose the model during tunnel start, retract to the tunnel wall after the shock passed, remain there during the valid test period, and extend to the closed position again before tunnel unstart. These protective plates have reduced transient loading an estimated 75% in the Mach 2 region and 50% in the Mach 3 region. They have also allowed successful testing of both the sting-mounted stabilizer and the complete vehicle model. Transient response measurements were made at various tunnel conditions for the pneumatically operated store ejection mechanism and for the motor-driven movable elevators with a snap-back spring. This program demonstrated that relatively fragile models could be tested in unevacuated blowdown wind tunnels at high Mach numbers and high dynamic pressures. The sting-mounted stabilizers and the complete vehicle demonstrated flutter margins throughout the mission profile. Transient structural dynamic loads on the model fuselage due to the ejection of an internal store and due to step elevator inputs were measured successfully. These accomplishments successfully completed all objectives of the dynamic model program. Further utilization of the dynamically similar model can be realized with the proposed aeroelastic model program for measurement of flexible aerodynamic derivatives. To resolve uncertainties in the penetration of neutrons through the zirconium hydride shadow shield, an experiment was performed at the General Atomic Division of General Dynamics. Here, high-energy electrons are generated and forced into an experimental cave, where neutrons are produced by secondary interactions. Inside the cave, a lead target was positioned at the projected intersection of the electron beam tube and the neutron drift tube. The high-energy electrons emerge from the beam tube and strike the lead target, producing neutrons and gamma rays. Some of these neutrons and gamma rays penetrate the shield and travel the 50-meter length of the collimated drift tube. Measurements of the energy distribution of the neutrons is then determined by their flight time down the tube. At the far end of the tube, the neutrons are measured by liquid xylene and boron trifluoride detectors, depending on the neutron energy range. Flight times are then converted and stored in a 1024 channel analyzer. Measurements were made on shields with thicknesses of 50, 86, and 125 grams per square centimeter, respectively. The 86 grams per square centimeter thickness was rotated to measure the angular distribution of the penetrating neutrons. The test substantiated the selection of zirconium hydride for the shadow shield and confirmed the fact that the shield could be designed and built with absolute certainty as to its neutron attenuation capability. In the area of servo control systems, Marquardt advanced the technology required for reliable operation at the high temperatures of the nuclear ramjet. A pneumatic servo system designed for 1200 degrees Fahrenheit operation was investigated. Test hardware consisted of a pulse width modulating servo control valve, which operates a hybrid gear pneumatic motor. The servo control valve is driven by an electrical torque motor. This system can be used to actuate inlet starting doors, bypass doors, and reactor control rods. After each component had been individually tested at both room temperature and at 1070 degrees Fahrenheit, it was integrated into the system for closed-loop operation. For high-temperature testing, the torque motor, servo control valve, and hybrid gear motor were enclosed in an oven. After being run as a closed loop for 6 hours at temperatures of 1070 degrees Fahrenheit or higher, the electro-pneumatic servo system was still operational. Although the electrical elements of the electro-pneumatic system offer advantages with regard to system response and compensation devices, reliability in the high-temperature nuclear environment is questionable. An all-pneumatic mechanical-pneumatic substitute for the electrical torque motor and pulse-width servo control valve was developed to increase system reliability. The mechanical components were designed to be interchangeable with the electrical hardware. The pneumatic mechanical system was also tested in closed-loop operation at 1070 degrees Fahrenheit. Other areas covered by the propulsion system contractor were system performance, aerothermodynamics, and structures. These investigations advanced the technology required for a nuclear ramjet-powered vehicle that incorporates existing Tory 2C reactor technology as designated by the Lawrence Radiation Laboratory. Significant achievements at Marquardt included Lawrence Radiation Laboratory's agreement that suggested Tory 2C reactor changes would increase engine thrust, selection of the double scoop configuration and continued model development, fabrication and successful testing at 1200 degrees Fahrenheit of an electro-pneumatic servo control system, and the further development testing of low-friction, high-temperature bearings. Back at Vought, material studies under the current contract specifically covered further design allowables work for PH15-7MO, establishment of data trends for Rene 41 sheet, screening of high-temperature lubrication systems, and screening of high-temperature sealant systems. In addition to the bearing test by Marquardt, in which bearings were spray-coated with lead oxide, dried and cured at high temperatures, 19 high-temperature lubricant systems were screened at LTV in empirical tests. These allowed relative ranking from the standpoint of lubricity and wear. The completed tests will allow selection of lubricant systems for initial prototype bearing tests. The primary purpose of high-temperature sealant tests was to determine the sealing potential of materials submitted by major laboratories. 15 separate systems were evaluated using diversified application techniques. The desired target property was the ability to seal 120 psig for 10 hours at 1000 degrees Fahrenheit. No material met this requirement, accenting the need for further development and investigation of a high-temperature sealant capable of withstanding the 1500 degrees Fahrenheit temperature of the low-altitude supersonic vehicle. Typical fuselage panels of the vehicle were tested under a combined thermal acoustic environment to determine fatigue effects during low-altitude supersonic flight. 6 configurations of the PH15-7MO panels were tested at the NASA Langley Research Center high-intensity noise facility. Tests consisted of 10 hours exposure to 162 decibel random noise and 1000 degrees Fahrenheit, typical environmental conditions anticipated for the vehicle. Of 6 panels tested, only 1 major failure was observed. Several small cracks developed in most of the panels during the 10 hours running time. Although results of material tests have been favorable, conclusions indicate that additional tests will be necessary to adequately define an optimum structure for the thermal acoustic environment. Subsystems in the nuclear ramjet missile must operate reliably while subjected to intense levels of neutron and gamma radiation. A continuing study and experimental program of the effects of nuclear radiation on avionics components was a major part of the LASV-N1 contract. 2 radiation effects tests were conducted during the LASV-N1 contract period. Both tests were performed in the Air Force's 3-megawatt nuclear aerospace research facility at Fort Worth. Radiation effects test number 8 was started on July 8th, and test number 9 was started on October 12th. The test articles in operation were evaluated while subjected to integrated neutron fluxes ranging up to 3 times 10 to the 17th neutrons per square centimeter and gamma doses up to 10 to the 11th ergs per gram carbon. Of particular importance was the use of a data management system to control, record, and analyze the radiation effects data during the test. The system uses a high-speed SDS 920 computer. Over 10 million individual data points were acquired and analyzed during radiation effects test number 9. Although the data from the tests are still undergoing comprehensive analysis, several significant conclusions are already evident. In test number 8, Test items such as the Burroughs and Sperry computer circuits operated properly to nuclear radiation levels equal to or exceeding their design goals. In test number 9, it was possible to dynamically evaluate inertial grade gyros and accelerometers and the associated platform electronics in the nuclear environment. The gyro and accelerometers had degraded signals, but were capable of closed-loop servo operation throughout the test. The PCM telemetry systems operated well beyond their design goals. 3 different voltage regulator designs were successfully tested. Magnetic and tunnel diode computer logic circuitry operated throughout the test. Degradation in some of the magnetic logic circuits was not experienced until levels reached twice the value of the nuclear design goals. Successful operation of tunnel diode computer circuits was accomplished at nuclear radiation exposures in excess of the LASV-N1 design goals. Critical components from each avionics subsystem were evaluated. Future work is progressing toward combined environmental testing of integrated subsystem components and parts. The internal environment and mission of the LASV vehicle demand a highly reliable radiation-resistant digital computer with navigation, guidance, and bombing capabilities. The Sperry design has replaced transistors which proved inadequate in the radiation environment of LASV with ceramic tubes. The tubes possess sufficient radiation resistance to assure reliable operation. Additional studies of radiation test data and basic circuit development have established that passive elements such as resistors and capacitors are adequately radiation resistant. To further evaluate radiation tolerance, this special component test fixture was fabricated and tested to establish applicability of these components for the LASV program. Computer implementation techniques accomplished by Burroughs Laboratories included the fabrication and testing of tunnel emission devices, thin film parametrons, and magnetic core ropes. Thin film tunnel diodes were formed in this deposit station vacuum chamber by the vapor deposition of metals and insulating materials on 3-inch by 1-inch glass slides. The deposit materials are contained in the boat turret. Directly above are the mask holder for the selected patterns. The substrate slides of glass or quartz are inserted into the holders near the top of the chamber, after which it may be anodized. A thin film parametron fabricated for the LASV-N1 program is shown here in various stages of completion. Magnetic core ropes were also fabricated and tested by Burroughs. Punched cards automatically select a pattern of cores through which the rope is wired. This is a completed core rope. And this is a close-up of an individual core. Radiation effects testing of the various components and circuits was accomplished at the Penn State Nuclear Reactor Facility. All components except the field effect devices showed satisfactory radiation tolerance to the design level. Autonetics, a division of North American Aviation, is currently involved in development of the attitude reference system of the LASV-N1 vehicle. The 2 gyros, which comprise the major components of the system, have undergone varied tests to determine proper operation after exposure to radiation. This is the accelerometer test equipment and radiation-resistant components. 2 of these pick-off transformers are used for each gyro. The transformer's innermost part is the core, which is wrapped in fine copper wire. The BOMAC division of Varian Associates has been engaged in studying microwave components for testing in a nuclear environment. A magnetometer is used to measure magnetization of ferrite samples. This is a prototype ferromagnetic mixer preamplifier, specially designed to eliminate the use of semiconductor elements to increase the radiation resistance of the mixer. A radiation-hardened ferrite isolator has been fabricated by bonding the metallic ferrite to the waveguide. This reduces radiation damage caused by organic agents, usually in isolator construction. Model antenna pattern measurements for the telemetry, radio command control, and tracking beacon subsystems were conducted by LTV Temco Aerosystems Division using a 1/8 scale model and a 1/5 scale model. For each of the 3 subsystems, an annular slot antenna was mounted on the bottom of the vehicle. The results of the tests indicate that favorable pattern coverage can be obtained with these antenna configurations. Radar cross-section measurements for the axisymmetric inlet configuration of LASV were measured using a 1/8 scale model. Similar measurements were made in 1962 on the double scoop inlet configuration. The tests accomplished in 1963 on the axisymmetric inlet were conducted to allow direct comparisons. Humphrey Incorporated has fabricated radiation-hardened rate gyros. One of these gyros is shown being operated on the rate table during a rate range test. The rate gyro output is nulled out using the ratio box and calibrated against a known value to measure accuracy. The motion is then stopped and the null value is checked. A slight movement of the table shows the sensitivity of the gyro. These are the completed gyros mounted on the test table with the deflection output and the gyro rate output recorded for analysis. At Molecular Research Incorporated, work continued on the PCM telemetry breadboard. This is a programmer unit specifically constructed as an interface unit between a PCM telemetry system and an instrumentation computer. The research and technology effort, which was conducted under the LASV-N1 contract, has to a great extent demonstrated the feasibility and credibility of advanced technology for a nuclear ramjet-powered vehicle. Establishment of flight test as an objective will enable this assembled industrial team to coordinate the individual effort required for early successful nuclear flight.